Okay, let me just refresh your memory. We started 16.1, concept of magnetic field. Just say that if there's a magnetic field around, we just need a current carrying conductor or permanent magnet. If there's a force acting on the current carrying conductor or permanent magnet, then we know there's a magnetic field. Then for a moving charge, we want to find the direction of the force on a moving charge. Remember, the charge must be moving at an angle, not parallel. If it's moving parallel to the field, there's no force at all. Right? Only at an angle, and there's a force given by this equation. To get the direction of this force, we use Fleming's left-hand rule. As I say, you can play with how to remember. You can call it McDonald for motion, fry for field, chicken for current. Okay, motion or force. That means left-hand rule give you the direction of the force on the moving charge. So that's the equation you need to remember. Then we say that if it's moving a magnetic field, then it will move into a circle of radius given by that equation. Right? The easiest way is not to memorize this formula, to remember that it's magnetic force equals centripetal force and derive this equation. Then after that, we look at force on current carrying conductor, right? Where we got this formula. There's a conductor carrying current I. And the field is at an angle to the conductor. So the force is BIL. We can use the same Fleming's left-hand rule, get the direction of the force. And Saturday, we did magnetic field due to current. Right? We look at current carrying conductor. There's the equation, you have to memorize all of them. Then we look at Ampere's law. We use Ampere's law to derive the current, this formula. And then we look at loop, a loop or a coil. That is the formula for the field at the center of the loop. Then we look at solenoid. If the solenoid is air core, then you can put this one as 1. If the solenoid is made of iron, then you have to put ferromagnetic material or iron, you have to put mu r. Okay, so today we are just extending that. That's all. We have said that that is the field due to this current carrying conductor. Just like this one, it is carry a current, so it has this field there. Then I put another conductor there. The conductor will be in this field, it will experience a force. You're just using this formula. Right? Force between two current carrying conductor. Derive and use this formula. Sorry. Derive and use this formula for force between two parallel current carrying conductor. Right? So we haven't completed it. We still got 2 more sections. We are basically using back force on current moving magnetic field, electric field here, and then we are going to apply it to Hall effect. Okay, so if you have the book, this is the book that we are using. You can turn to page 166 to 169. Force between current carrying conductors. Okay, basically, it's summarized for you in this picture. This conductor has a field around it, given by this formula. And place another conductor there. Then the force on this conductor in this field there is just your I2, this is your I2, times your delta L. Delta L just take a small section, or L of the length, that L there, times your B. Right? So it's just placing this B inside here, you get this equation. And then we will get this result, like current attract. These two current, they are in the same direction, they attract. Whereas light charges repel, remember that. Okay. You have to memorize the formula, right? Not given you. A level, they are given you. They have a conductor, the field around the conductor at a distance, perpendicular distance r away, is given by this formula. Then show that the force on another conductor, another wire or conductor carrying current I2 in the same direction, a distance d is given by this equation. Right? We are going to derive this equation. Right? Remember, the current, we have our right hand grip rule. Right? When you grip the conductor, the thumb will be in the direction of the current, and the field will be in concentric circle, and the direction of the field is given by your fingers, direction of fingers. Okay, that's given clearly here. So we show it here. Okay, so that conductor carrying a current I, the field is given by this formula. Right? R is the perpendicular distance. Now we place another conductor there. Wire 2 or conductor 2. So the force on this conductor, right, wire 2, is just your that field due to wire 1 times your current in I2 times your length of wire 2. Okay, so now we call the D the separation, which is the same as R here, same thing. That's your I2. And we can call it a small section there. L or delta L, doesn't matter. Right? Delta L means a small section. Now we can replace B with that equation there. Okay. And I2 is this conductor. You look at this conductor in the field. That's the field. B times your length. That is the length. Okay. So that's our equation. Take our length down. So we call that force per unit length. Mu naught I2 2 pi D. Right? We change the R to D, that's all. Because it's given D is a separation. Right? That is if you imagine 3 dimension. Okay, we'll try to get this result soon. Like current attract. Right? So this is called force per unit length. Okay, so you can look at 2 dimension. Same, we are looking at the same thing, the same derivation. We are just showing you can look at 2 dimension. Force on wire 2 in magnetic field B. Right? Remember the wire 1 is the one that contributes to the field. So we can remove that and put that right hand curve rule, right hand grip rule, sorry. Right? It's going into a circle. So at this point there, it's going in. Right? The arrow tail show it's going in. So it's given a B I2 L. We are looking at this conductor. Right? L is the length of short length of this conductor. And B given and your I2. That's how we derive our equation. Okay. How to get the direction of the force? Use your Fleming's left hand rule. Your field is going in. Field is going in. Field is going in. That's your field. D current going in. Field is going in. Your current is going up. So that's your force. Can use your finger. Use your finger. Learn yourself. There's your current going up. There's your field going in. Current going up. Field going in.
Fleming's left hand rule.
Fleming's left hand rule. Can or not? Yeah. Can or not? Can or not? There's your
Wait. Okay, the second finger up, and then the
Second finger up. First finger into the
magnetic.
page, into the screen.
Okay.
Then you
So
should,
it's coming in lah.
the force should go to the left.
Oh yeah, to the left.
Okay. Yeah.
Ah yes, force going to the left.
Okay. So you can try it for unlike current also. Right? That's your homework.
Does it look like this? Wait, I show.
This is going in. Current is going. Yeah.
Then the middle finger is going up, the current.
Yeah. Second finger is going up, and then the first
No. Thumb is going left, right?
yeah, thumb is going left.
And then middle finger, I mean second finger is going up the current.
That's
Then
right.
this one is going in, right?
Yeah, the field is going in. The first finger is going in.
Okay.
Yeah, sure. You can try for unlike current. We will do some exercise later on. Okay, so we have got the equation. Now we want to define ampere. Okay, you can call it I1 or I, doesn't matter. That is the equation that we have derived. Right? Substituting, let I1, I2 be 1 ampere and the separation in 1 meter. Right? Put in the value of mu naught 4 pi times 10 to the power minus 7. I1, I2 is 1, 2 pi. Right? This is 1 meter. Cancel that, you still got a 2 there. So we get 2 times 10 to the power minus 7 Newton meter minus what? So now we can define ampere. 1 ampere is the value of the steady current in 2 straight infinitely long conductor of negligible cross-sectional area separated by 1 meter in vacuum. And it experiences a force per unit length of 2 times 10 to the power minus 7 Newton meter minus 1. That's how we define ampere. Okay, basic idea is 2 infinitely long conductor, diameter negligible, that means very, very thin, and 1 meter apart. The force per in vacuum, the conductor is placed in vacuum parallel to each other, and that is the value of the force per meter. Okay, memory work, nothing much. Know how you derive the ampere, that's all. That means our ammeter, if we want to check the current, then that is what we do. Right? Usually we don't bother to check, we just assume it's correct. Normally it will age because the magnet becomes weaker. Okay, we have more or less completed. We will do some example. Comparison of electric and magnetic field and gravitational field. Right? If you have electric field like this one, right? Electric field very straightforward, 2 dimension only. Right? Remember the field is the motion or the force on the positive charge. So the positive charge will move in the direction of the field, negative charge opposite direction. Right? So in the electric field, a charge small mass experience a force. Positive charge mass move in the direction of the field, while negative one move in opposite direction. Right? Here's gravity, G, pulling you down. Doesn't matter about the shape of the mass. It will always move downwards, only one. Right? In gravitation field, uncharged mass experience a force. And the force on the mass is given by the formula W equals to mg. In magnetic field, a charge, magnetic field, if it's moving in a direction, as a field or opposite direction, there's no force. Right? So the charge will only experience a force if it's moving at an angle to the field, not parallel. In magnetic field, there's no force on charged mass when it is stationary. If it's not moving, no force. Right? So the requirement is it must be moving, not parallel, Arrow, if it's stationary, it doesn't experience any force. It must be moving at an angle to the field. Then it will experience a force. Okay, so if you have a field going in, you get positive and negative charge, they will be deflected in different directions as well. If both of them have the same mass, right? But opposite charge. Okay, so we have more or less completed. Let's do some question. Right? That's a new formula that you are supposed to learn to use and memorize. Right? And that's what we will be using, like current attract and like current repel. Right? Same different direction current, they repel each other. Okay, what is the answer for this one? A small flat coil lies inside a similar large piece, a large one. Right? We view from above, or we call plane view. There's a smaller one. Each coil carry a current as shown. Current is shown there. What is experienced by the small coil due to the current? Yeah. Just applying what you have learned. What happened to we have light? What happened if we have light current?
A? B, sorry, B.
How to have a torque? A torque means you must have two forces there.
Yeah. Oh, no. Donkey. Sorry, donkey.
Why donkey?
Both of them going same direction.
Huh? What do you mean go both of them going same direction?
No, the small coil and the large coil, you all rotating similarly.
Yeah, the current is same direction. So what happened?
C?
I know D, but why I'm asking you why? Yeah, must be a reasoning, not simply a guessing work. Yeah. Can?
When current same direction, there is force of attraction between the two wires.
These are why you call light current. Right? If you look at a vertical line, light current, this is the attractive force, that means the force is going up. Between these two, there's also an attractive force, so it means it's going down. So the two forces are equal and opposite, so they balance each other, so no resultant force. Okay, that's the reason. Light current attract, you can take on this side, this line there, the same thing. This will be pulled to the right, this side will be pulled to the left, so they are equal and opposite. Okay, good.
Wait, I don't understand. 1 minute. Wait. So they only no resultant force, but if they repulse, they got resultant force. That got make sense, sir.
No resultant force because it's equal and opposite.
No, but if it's repulsion means outcome is not no resultant force. Why is it like God resultant force? It's already far away. Right? If.
Basically, we are just using this idea, that's all. Right? We are just using this formula. If they are in the same direction, there's attractive force between them. So in this circle, all around, there are attractive force there. Right? This part there, if you look horizontally, between these two, there's attractive force there. That means the small circle is pulled out here. Here, the small circle is also pulled out to the left. So both forces are the same magnitude. Because the distance is the same, the current is the same. And yeah, just using like current attract as well. Yep. What's the problem? What is the problem?
No, okay.
Right? Idea is we are just using what we have learned. Right? The light current, the gap is the same.
Hello?
Yeah. Okay. The gap is the same, or the distance apart is the same. So the force is the same magnitude, but opposite direction as well. Okay, this one we will try that. Two long straight current carrying conductor, this one, PQ and XY, are held in a constant distance apart. That's a distance apart. It's your figure there. The conductors each carry the same current, current I in the same direction. A plane view above, you're looking from the top there. There's your one wire, there's the other conductor. Both of them are coming out, showing us a point. On figure 6.2, draw arrows, one in each case, to show the direction of the magnetic field of Q due to the current in XY. Label that B. Right? This is a current. It has a field. So we want to draw the field due to this wire on this conductor Q. How to draw? What should it be? Okay? Just applying the Saturday lesson where we learn the field using your right hand grip rule. Can?
Right hand grip rule.
Yeah. We are just using
the solenoid one.
that one, just to get the direction of the field around the current carrying conductor.
The thumb is the current, right?
Thumb is the current. Okay. So
And
this one is looking at three
other
dimensions.
fingers are the magnetic field, right?
The thumb represents your current. So the field is circular.
No. I mean the other. Yeah, the fingers. Yes.
The field is circular. So direction is given by the finger. Yeah. Where should it be here? Where is the field due to this conductor? Drawing here, we are looking at 2 dimensions rather than 3 dimensions.
Teacher, something wrong with your internet. Can't hear you.
Can't hear me? What's wrong? I'm okay. I can.
No, suddenly your side there lagging or something. I don't know why.
Maybe the internet is not stable. No?
Okay, now can.
I think the internet is not stable. Okay, so where's the field? Where's your B here?
My B. This is coming in, right? So
this is coming out. Coming out. Ah.
Oh, the X is coming in.
Oh, yeah, XY, this way, coming out.
So you're asking me where's the force?
You want the field at B, at this conductor there.
Oh,
where is your B?
Where is my B?
Yeah. You should know that it's all circular.
Yeah, it's circular.
And then get the direction.
You want me to tell whether it's clockwise or anti-clockwise, right?
No, I just want it here. Is it a circle or straight line, or where's the straight line? Where's the actual straight line or what? That's all.
Oh, it's a straight line.
Where does it go? Left, right, up, down?
Right. Yeah, right.
You are wrong. Right? The field is circular.
Circle.
And if you look at here, where's the direction? Right hand grip rule is going anti-clockwise. So that's where it goes. But we are looking at
it's going right.
Point here. Point here means you want a tangent. Right? Tangent. Not a circle. You want a tangent. At that point there, at the Q there is a tangent to the circle. There's a big circle coming down there. Right? We are looking at that tangent there. So Q will be going down there, B. There. That's all. So now applying, you got a field, you got a current coming out. Where's the direction of the force? Using your Fleming's left-hand rule.
The direction of the
is going
force.
down. The current is coming out. Yeah, field is going down. Current is coming out. Where's the direction of the force? Up, down, in, out, left, right.
The force is going to the left.
You point your finger wrongly already. The field is going down. The field is going down.
Yes, field going
The current
down.
is coming out. So where's the thumb? Left-hand rule.
Okay, field is going down. Current is going up. So why my finger damn weird one? Wait.
That's why I say use right hand palm rule easier.
Like this.
Going down. Current is coming out. You can go straight. Slapping people easier to remember. Easier to turn your fingers or your hand. Left hand is harder to turn. Palm is easier.
Wait. Okay. Left hand.
Field is going down.
Wait.
Current is coming out.
Field going down. Okay. Current coming out.
Current is coming out. Make sure you know how to read. Field is going down.
Like this.
Yeah. Hey, how come your field is going up? Your field should be going down. Show again.
Okay. No.
Field is going down. Current is coming out. Okay, correct. So it should be to the right. Can. Just draw, that's all. That's the force.
Yeah, coming out. Field to the right. Yeah. Force to the right.
Okay.
Force to the right. Okay.
Right. Make sure you know how to draw the field. State Newton's third law. You can remember.
Oh, action, reaction.
No action and reaction. You state it properly. When two bodies interact, the force on one.
But body is equal but opposite in direction.
Change a new zoom soon. Force on one body is
so
equal
fast,
or opposite in direction to the force on the other body. Okay, this is the action and reaction force. Basically, they are asking you in this question.
Yeah.
Use the law and your answer in A2 to state the direction of the force on XY. Okay, now that's the force on XY. Yep. Using your Newton's third law, force on XY. On your Q is to the right. So that where's the reaction force on the Y? Equal but opposite. Yeah. So it must be to the left or right?
Wait. Force.
Too slow, can wait for you. It must be to the. This is to the left. That must be to the right. That's all.
Yeah.
That's the problem. Action and reaction force.
Opposite.
Okay. Any question on that?
No.
If not, you can look at this question.
Yes.
I'm going to change a new zoom. This one we are going to look at the field here and the force here. That's all. Okay, we
Okay.
can capture that. I'm going to switch it off. Start a new loop. You can take 5 minutes break.
Okay.
Okay.
Okay. So you're going to start in 5 minutes or 10 minutes?
5 minutes, 5 minutes.
Okay. Okay.